Hello, and welcome to the next part of our unit on magnetism. In this part, we're going to look at the magnetic field due to a current carrying wire. The phenomena that a current carrying wire produces a magnetic field was first discovered by Ørsted. He was in the process of putting together a demonstration for his students when he had a compass near a wire, and he noticed that when the wire had a current, the compass deflected, and when it did not, nothing happened. This is now known as Ørsted's experiment. Again, it's because a compass deflects near a current carrying wire. Through that experiment, they discovered that the magnetic field formed a loop or a complete circle around the wire. Because the magnetic field is a full circle, there are no magnetic poles present. The direction of the magnetic field is determined by right-hand rule A. I'm going to briefly introduce right-hand rule A here, but I will refer you to the last part of this unit where I do many examples where you can actually see my hand as I perform the right-hand rule. So the right-hand rule A is for finding the direction of the field due to a current carrying wire. Your thumb points in the direction of the current, and then your fingers kind of curl around to give you the direction of the field. I have two examples here on this page. The first on the left has the current in a wire, and the current is coming out of the page or out of the screen at you. So if you stick your thumb at yourself, your fingers form a circle kind of around your thumb that is going counterclockwise. On the right, we have the opposite case where the current is going into the page. So stick your thumb away from you, and now your fingers form a circle that goes clockwise around your thumb, as illustrated here. Once the connection between electricity and magnetism was found, it immediately began to be exploited, and one of the very, very first electromagnets developed is known as a solenoid. If you open this simulation, you see this. If you turn off the battery, no magnetic field. If you turn it on just a little bit, you get a magnetic field, but if you turn on the battery more, the field gets stronger, and that is because the bigger battery here causes a larger current, and a larger current creates a larger magnetic field. You can also change the number of loops, and hopefully you can tell that as the number of loops have gotten smaller, the magnetic field has gotten weaker. That's because as you add the loops up, you get more accumulated current, if you will. The other thing to notice here is that in very many ways, the magnetic field due to a solenoid looks a lot like the magnetic field due to a bar magnet. So anything you could imagine doing with a bar magnet, you can also perform with a solenoid. So summarizing, the magnetic field due to or in a solenoid due to a solenoid increases if you increase the current through the wire. It increases if you add more turns, and it looks like the field due to a bar magnet. This is exploited in very many ways, but one that is very easy to image is a large magnet used to pick up junk. So inside this disc is a bunch of coils of wire. This cord coming in is probably the power cord to the electromagnet, be my guess, because it doesn't look like it has any tension on it. In order to pick up the junk, you turn on the electromagnet, start passing a current through it. You can then raise it up, move it to the side. My guess is this is a horizontal positioning wire. And then once you have relocated the metallic portions of the junk, you can drop it. Now, my guess is one of two things happens. One option is that they just turn the electromagnetic off, so make the current zero in it. But remember that if an object sits in a strong magnetic field for any length of time, it too becomes a magnet. So turning the electromagnet off may not be sufficient to actually get everything to drop. But if you reverse the polarity so that the current flows the other way through the electromagnet, you're going to go from things that attract to things that repel, and it will kind of force things to drop off the electromagnet. This concludes this part of this unit. In the next part, we're going to look at the force on a current, or force on a moving charge in a magnetic field.